Earlier we learned how to conduct a one-way ANOVA. When we say one way, we mean that there is only one independent variable. Specifically, we're talking about a categorical independent variable, aka factor. However, you could have a situation where you're interested in more than one predictor, more than one categorical predictor. It's possible to analyze the influence of two or more factors at the same time. Whenever we have more than one factor in the model, we call that a factorial ANOVA. A factorial ANOVA. So let's take a look at an example. Suppose you were interested in studying the effect of computers on people's everyday life. Specifically, you want to know if using computers saves people time. So you decide to conduct an experiment. Some people perform a task by hand, while others perform the same task using a computer. Now you also decide, I think that it's not just about whether or not they use a computer. I think it's going to have something to do with the complexity of the task. So in your experiment, you have some people perform a simple task, making a grocery list. Other people in your experiment will perform a complicated task, in this case, calculating an ANOVA statistic by hand. This would be an example of a 2 by 2 factorial ANOVA, because there are two factors with two levels of each. So the first factor is computer use. The second factor is task complexity. So both of these are independent variables. They're both categorical independent variables, and each one has two levels. So with computer use, you could either use the computer or not use the computer. If this were not a factorial situation, then you would have an experiment with just two conditions. In this case, all you would need would be a t-test. But we have another factor, the complexity of the task. So at level 1, it's a simple task. They make a grocery list. At the other level, they do a more complicated task, that is, calculate an ANOVA statistic. So there are 4 different conditions in this experiment, and here's how you would diagram it. So factor 1 is computer use, factor 2 is task complexity. So in one condition, you'd have someone do a simple task with a computer. In another condition, they would do a simple task without the computer. And then another condition, they would do a complex task with a computer. And then finally, a complex task without the computer. So you'd have a certain number of participants, and you randomly assign them to one of these 4 conditions. When we run a factorial ANOVA, we can determine the influence of each variable independently. And this is what's called the main effect. So for example, if the use of a computer affects how quickly the task is completed, we'd say there is a main effect for computer use. On the other hand, if it didn't matter whether or not they used a computer, the means are the same, we'd say there is no main effect for computer use. You could say the same thing about task complexity. An interaction is when the effect of one variable depends on the level of another variable. In our example, each variable has 2 levels. There's 2 levels of computer use, and there's 2 levels of task complexity. So if the computer helps with one complexity of task but not the other one, that's what we call an interaction effect. So how do you run a factorial ANOVA? Well, you actually have to use a different option. So before, for an ANOVA, you'd use compare means. Now we go down to GLM, or general linear model. And we're going to choose univariate. And univariate, when you say uni obviously means one, multi meaning more than one. This refers to the dependent variable. So here we're looking at one dependent variable. These are all univariate statistics. And you click on that guy, and you're going to get a window that looks like this. And you have your dependent variable just like before, but now you can see that there's room for more than one factor, because this allows you to run a factorial ANOVA. So with the regular one-way ANOVA, there's only room for one factor. Now there's room for more, and you can actually add quite a few. So in this case, we're using computer use and task complexity. These are called fixed factors because they're in discrete levels. You've assigned people to groups. If there is an interaction effect, it's not terribly intuitive all the time, and it can be hard to understand. So there are ways to plot a graph to help make sense out of an interaction, to see what it looks like visually. So when you click the plots button, it allows you to do that. So you have the factors here to choose from, and you can choose a horizontal axis, and then in this case, instead of just the y-axis is going to be your task completion time. So instead of, what you'll have to do is actually have separate lines. You'll see in a second. So you can tell it which variable goes on separate lines and which goes on the x-axis. So what we're telling it here is that I want the task complexity to be on the x-axis, the task completion time on the y-axis, and we'll have a separate line for with the computer and without the computer. So you have to hit add, so it shows up down here, and continue, and then you click OK. So here's what the output box looks like for a factorial ANOVA. There's a lot of numbers here, and it gets a little confusing. So the first line, corrected model, you can ignore that. The intercept, you can ignore that. And at the bottom, error, total, and corrected total, you can ignore all of that. All we care about is these three middle ones right here. Comp use, complexity, and computer use times, that's an asterisk, which stands for times, complexity. This is a product term, and product terms are used to symbolize an interaction effect. So we look at these individually. So first we look at computer use. And you can just, this looks familiar, right? Your sum of squares, your F statistic, and so forth. So we go to significance level 0.002. So that means there's a significant main effect for computer use. So computer use does matter, right? Using a computer saves time. All else being equal, computer use makes a difference. Now we go down to complexity. Same thing, we see that it's significant, 0.000. So task complexity does make a difference. Whether or not you're completing a simple or a complex task is going to affect how long it takes you to do it. So there's a significant main effect for complexity. All else being equal, complexity matters. This last one, this is what's probably new to you. This is the interaction term. In this case, it's also significant, 0.000. Right? So there is a significant interaction. The effect of one variable changes based on the level of the other variable. Now you're probably a little confused by that, so let's take a look at the plot. That's going to make a little more sense. So here's the plot of the situation. This is the mean task completion time. This is 10 minutes to 30 minutes. Here's for simple tasks. Here's for complex tasks. This is the grocery list. This is the complicated math problem. The blue are the people who use the computer, and the green are the people who did not use the computer. And whenever these lines are not parallel, that represents an interaction. These cross. They don't actually technically have to cross as long as they're not parallel. Like if these, even if they were, the green was always on top and the blue is on the bottom, as long as they diverge, that's an interaction. So how do we interpret this? Well, the green is without the computer. So without the computer, you can make a grocery list by hand really quick. Maybe a few minutes to think of what you're going to buy, write it down, you're done. But to compute a hard math problem by hand without the computer, that's going to take a really long time, maybe 26, 27 minutes just to do one problem if it's a hard problem. Now with the computer, well, you notice it actually took them longer to do the grocery list with the computer. So maybe some of the participants weren't that skilled with a computer. They had to open up Word and maybe it had to update something, or there was a problem and maybe they didn't know how to save or print it. Their printer was out of paper and they had to find some paper. Who knows? But it actually took longer to make the grocery list with the computer. But when they came to do the difficult task, the hard math problem, people that used the computer did it way faster. So they still probably had to figure some things out, 20 minutes. Maybe they had to look at the instructions and load the software. But when it came down to it, it was still way faster than doing it by hand on average. So this is an interaction. So do computers save you time? The answer, it depends. Are we doing a simple task or a hard task? In other words, computers make easy things hard and hard things easy. So here it is sort of blown up. The people who use the computer took longer to complete the task, but the people who use the computer finished the more difficult task more quickly. Right? So does computer use save time? It depends. Whenever the answer is it depends, that is an interaction effect.